Hello, everybody. Welcome to my talk. I'm going to discuss an overview of goals and approaches to radiocarbon dating. It's very nice to speak to you today in a very wet and miserable Dublin. My name is Andrew Parnell. I'm a professor in statistics at Maynooth University in Ireland. I've been asked to talk about this kind of general topic as an overview, but my real expertise, as I said, is in statistics. So I'm going to focus on more of the data aspect and the modeling aspects of these kind of approaches. I thought I'd split this talk into two parts. The first part is just a set of slides. There's about 6 or 7 of them, where I'm going to talk through some of the main ideas that you're going to cover, not just in my talk, but in a number of the other talks as well. And then in the second half, I thought I'd give you a quick demo using one of my R packages, Bchron, to just show you the kind of things that you can do and the issues that you can face. But really, this is meant as a setup for other talks so that you can get the most out of everything together. So in my experience, the kind of things that people want to create when they're using radiocarbon dates and age depth models in paleoenvironmental, specifically sort of coastal and sea level change, these are the kind of things that people want to create. So this is from a paper we published a few years ago. The lead author was Andy Kemp. I think it's in the Holocene. And it's going back in time. So you can see we've got years along the horizontal axis here. We've got relative sea level in meters. And the key thing in all of the projects that I'm involved in that we're trying to create is that yellow line that goes through the middle. That's our relative sea level curve. And the bit that most interests me and that I care most about is actually the blue bits around that yellow curve. So the uncertainty in that curve, where does that come from? How do we get it? And where does radiocarbon dating fit in to creating that yellow main fitted line and the blue uncertainty bars around it? And that's mostly what I'm going to talk about in the next few slides, how we get to this point. There's a little bit of left out stuff, or there's lots of left out stuff on this slide. The data points, I hope you can see my mouse if I wave it around here, are these circles here. And it looks like most of them are close to the line, which is good. Some of them are a little bit further away from the line, but really all of those little circles, those data points, have uncertainty in them. They have 2 types of uncertainty in them. They have vertical uncertainty because you don't know exactly what the sea level was at that particular point. And they have horizontal uncertainty because you also don't know exactly what the date of them was. And the tricky part for most of these kind of models and creating these kind of curves is how you take account of both of those 2 sources of uncertainty. Most of the ones I get involved with as well are usually for a single core. So this is one site. It might have a tide gauge record or something spliced onto one end of it. But usually it's sort of 1 or 2 cores, which are very, very close together. It's much more complicated to do this kind of thing, but it can be done. It's much more complicated to do this kind of thing when you have multiple cores and sites or a whole coastline that you're trying to stick together. So I'm going to assume that this is the kind of thing that you might want to create. Obviously, everybody's data and approach and background is different. So you might have slightly different goals, but this is roughly where I think you want to try and get to. So the steps that I think you want to create for these kind of projects is that you'd normally have 2 kind of data sets side by side, and there's a tricky thing of how you actually create those data sets in the first place, but you've got kind of 2 data sets. The first is a data set of sea level markers of various sorts, could be from all types of different methods. So sea level markers for individual depths down your core, and then for perhaps some of those depths where you've got the sea level markers, or perhaps none at all, you've got dates for them as well. And usually radiocarbon dates are a bit more expensive to create. So there's usually fewer dates than there are sea level markers, but not always. But almost always in all of the data sets that I've ever analyzed, the dates come from a different set of depths than the markers. Now, I'm not going to talk a huge amount about how you might date parts from your core. There are loads of other talks in this session. So talks 2 to 9, I think if you look at the one-page flyer that went out, are all dealing with sort of how you might choose dates, what the issues are with those kind of dates, and the other sort of more advanced techniques in that part of the data collection. Once you've got dates, be they radiocarbon or otherwise, you need to create an age depth model. And that's key because it enables you to date all of the sea level markers. Okay, so you've got sea level markers at a certain set of depths, you've got dates at another set of depths. This key thing called the age depth model enables you to match dates onto all the sea level markers. And that's what enables you to create those little circles in the previous slide, because then you can plot date against sea level. And I'm going to talk a little bit about that in this talk, but there's also 2 much more detailed talks on this later on. Talk 10, which covers radiocarbon dating in a bit more detail than I will, and talk 11, which covers age depth modeling in a bit more detail than I will as well. Once you've got that age depth model, you then need to use what I'm going to call a special regression model. So you've probably met linear regression before, which fits straight lines that best fit through the data. Usually you don't want a straight line when you want to estimate a sea level curve. You want something that's a bit more flexible. And people usually use 2 main methods for that, one called splines and another called Gaussian processes. But you also not only need to use a non-linear regression model, you also need to be able to take account of the uncertainties, both from the age depth model and also the uncertainty in the sea level markers. And I'm going to talk very, very briefly at the end of this talk about that, but that's the main focus of talk 12. So between those, my talk and those other talks, hopefully you'll get a really good handle on how you create that kind of plot from the previous slides. And of course, once you've got all of those, you want to create estimates of rates and accelerations and all kinds of other quantities of interest. But for me, the key thing that I always want to do if I'm estimating those kind of things is make sure I can do it with uncertainty. So I can create like a 95% confidence interval for my rate of sea level rise. That's what I'm really interested in, making sure that I've got that uncertainty actually correct, that it's not an overestimate or an underestimate of that uncertainty bound. So these are the techniques that we're going to talk about. I'm not really going to talk too much about obtaining the data set because there are a lot of other talks about how you might get those things, and it's really not my area of expertise. I'm going to talk a little bit more about the age depth models and a very, very small amount about these special regression models. I always prefer it if I can actually see the data. Okay, it's all very well looking at these beautiful, colorful plots, but for me, it's actually being able to see the numbers of what's going on in the background that enables me to understand really what's happening. I'm going to work you through, both in these slides and then in the little demo afterwards, I'm going to walk you through a real data set that comes with the Bchron package. And these 2 data sets are called test cron data and test RSL data. So the test cron data has a load of dates in it. Some of these are lead dates. Some of these are radiocarbon dates. There's some other weird ones, some tephras in here as well. And if you look at the different columns in here, so there's 27 rows, there's 27 dates for the chronology. The first 11 of them are lead dates. I'm not going to talk too much about lead dating. There might be other talks later on that cover a bit more. There's more detailed ways of analyzing it than I've done here. We've got the estimated age. We've got the estimated age standard deviation. We've got the position or the depth. So I use position and depth kind of interchangeably here. You've got the thickness of the layer that was dated. And then you've got the calibration curve. And here we've got different types of calibration curves. This example is a little bit old now. I'm still using IntCal 13. I could update this to IntCal 20 if I wanted to. There's 2 types of calibration curves in this particular data set. So there are normal Northern Hemisphere IntCal 13 dates, and there are what called normal dates. These don't require any kind of radiocarbon calibration. So these are just assumed to be exactly in years AD. The ones which require calibration are assumed to be in radiocarbon years before present, and therefore need calibration. So you can see we can go down the core here. So we've got ones at 0.5 centimetre, 1.5 centimetres, all the way down to 162 centimetres. We've got the names of the different types of dates. We've got their ages and their uncertainties. We've got the thickness of the layer that was sent for dating. And we've got the type of calibration curve that they require. So no calibration, essentially, or radiocarbon calibration. So that's the one half of the data set. That's what's going to enable us to create our age depth model. And this is the other half of the data set. So this actually says that the sea level markers. So this has a depth 3.5 centimeters. We have an estimated relative sea level of minus 0.0267. And there are uncertainties associated with all of these. And somewhat artificially here, these are all set at 0.2 centimeters. I'm not sure if that's entirely valid, but I can't remember where this data set came from. Anyway, so the idea is that we create an age depth model which enables us to estimate the age for these depths here. And that's what enables us to create that plot of age against sea level. And that's what we put into our special regression model to get our sea level curve and then the associated uncertainty with it. So these are the two main ingredients. Creating both of these is a huge amount of work, which I've completely skirted over. So how you choose which dates to depth, you want to get as many dates as you possibly can. You want to get them spread out throughout the core, unless you're particularly focused on a certain area where you really want to get the uncertainty down. And then also creating all kinds of these can involve all kinds of other methods to do with how you've actually created your sea level proxies and how you then transform them into sea level. And I'm not going to talk about either of those in this talk. So as I said, we've got some radiocarbon dates in our core, and radiocarbon dates come in radiocarbon years. And dates in radiocarbon years are assumed to be nice and normally distributed with a lovely bell-shaped curve. But unfortunately, the radiocarbon clock, as many of you will know, doesn't translate into the calendar clock in a nice way. It has this horrible thing called the calibration curve. Here it is here. So this is calendar age going backwards in time here. And this is radiocarbon age. And the calibration curve matches the two of those together. And whilst in radiocarbon years, everything is assumed to be nice and normally distributed. If you fire that uncertainty through the calibration curve, the actual true calendar age for an individual sample is really, really not normally distributed. It's very far from a normal distribution. So normal distributions are nice because you can summarize them with like the mean and the standard deviation. Calibrated radiocarbon dates are not nice. Summarizing them with a mean and a standard deviation is not helpful. People tend instead to pick out large chunks of the probability, and you should never ever report a calibrated radiocarbon date without estimates of uncertainty. So there's lots of different ways to create these. I'm not going to go into the bowels of the maths of how you actually compute these calibrated radiocarbon date distributions, but I'd be very happy to chat about it if people want to ask me to try and explain it. All you're essentially doing is firing this normal distribution through here, and you can see where you've got big wiggles, you end up with big wiggles down here as well in the calibrated date. So we can take each of those depths in the left-hand data set we had a couple of slides ago, and we can calibrate them. And this is the kind of plot that you get. So here we go, look, here are all the little lead dates at all. They require no calibration at all. It just ends up with the same age and the same standard deviation. And look, they're all really nice and narrow. But as you go back, you can see we've got things like our tephra age, you've got the other ages down the bottom as we get down to around 160 centimeters. And you can see we're going back about 2,000 years in this particular core here. So this is a very common age depth plot. We've got depth on the vertical axis, which makes most sense to me because you're going down your core, for example, going down 160 centimeters. You've got age going back from 0 years BP back to about 2,000 years before present. And you can see all of the horrible wiggliness of the calibrated radiocarbon dates once they've been fired through the calibration curve. And the task of an age depth model is, on the face of it, very simple. All it has to do is put a curve through these points. So we know the dates at certain places of the core. We want to be able to estimate the ages at other depths. So I'm going to be able to say, right, what's the age at 120 centimeters? And you can come back and tell me, oh, it's about 1,700 years before present. they have this key extra thing in them. They have to take account of the law of superposition. So as you go down the core, it has to be older. It's known in the trade as monotonic regression or isotonic regression occasionally. And there are lots of different methods that people have developed which enable you to put curves through this, which enforce the law of superposition, but they do clever things as well. They take account of the fact that you've got uncertainty in these and that it's really complicated, irregular uncertainty. And they also take account of the fact that occasionally you have slightly screwy dates in here. So you have dates that you kind of want to ignore. They either don't follow the law of superposition, so they must be wrong, or you've got a combination of dates, which kind of some of them might follow the right law, but some of them might not. And these models try to judge where the curve should go through to produce an age depth model. And I developed one of these called Bchron, but there are others out there as well that you should also learn about and explore. If you run the Bchron version of it on this data set, this is the kind of thing you get. So, okay, so the blue curve here, the black line is the best estimate, and the blue is the 95% uncertainty. So it's the same plot as before. Look, you can see all your little lead dates through here. And what Bchron has done in this has fitted a curve through these, which enforces the law of superposition. As you go down the core, it must get older, always. It takes account of all of these uncertainties in these radiocarbon dates. And what you'll tend to see is that it kind of pinches together. Where you've got lots of dates and lots of information, it gets narrower. But when you get to places where you haven't got much information, it bows out. The uncertainty gets bigger. And this is the kind of thing you can create. Once you've got this, you've now got the ability to look up any depth across the vertical axis and be able to get an estimated age and, most importantly, an estimated age uncertainty. And whilst radiocarbon dates tend to be quite irregular and horrible in their uncertainties, actually, once you create these age depth models, you usually find that they're a lot smoother. They're not nearly as horribly bumpy and all over the place as the radiocarbon calibrated dates. Once you've got that, of course, you can now create a plot like we started with at the beginning. So now for every single one of my sea level markers, I've now got an age and an uncertainty. So here, for example, ignore the fitted line and the dashed lines for a moment. Look at all these circles here. All of these little circles are an individual sea level marker with its vertical sea level uncertainty. Remember, they were all about 0.2. And now from the age depth model, they all have this horizontal uncertainty as well, because we've got that from the age depth model. And so we put that into a special regression model. Here I've fitted a one which comes with Bchron, which is called an errors in variables cubic regression. But in later talks, you're going to see much richer versions than this simple thing. And this just enables you to put a curve through it and some dotted uncertainty bands, which enable you to take account of both the uncertainty in the vertical direction for each of these circles and the horizontal direction as well. Okay, so that's a very whistle-stop tour. It's the kind of things that I would be involved in looking at radiocarbon dates and building age depth models and trying to turn that into a sea level curve. Obviously, you should now go and watch the other talks. So the other talks are on how to choose the date, how to actually get the date, how to process the samples and so on in a core. There's another talk on the background of age depth models, most likely in more detail than I've got here. And there's another really cool piece of software called Bchron, which you should learn, which is another R package, which enables you to create age depth models. And then there's a later talk as well on how to fit special regression models to account for uncertainty in the sea level markers and the age depth model. So all of these together should give you a really strong background as to how to get through it. Okay, so that was a very quick set of slides, but I thought I'd show you a quick demonstration of how to create all of those plots that I just showed essentially in Bchron. These slides and the code behind what I'm about to show you is all available on my GitHub site. So if you go to github.com/AndrewC.Parnell/radiocarbon workshop, you will find a page there which has the code and these slides, and you can see how everything works. I'm going to talk you through it very quickly now. If I just swap to share my screen and change to Safari. Hopefully you can see my screen again now. This is the GitHub repository, which has in it the PowerPoint slides, and it also has a file in here. So it's got a code, yeah, it's got a, which one is it? HTML file. If you double click on that one, it will bring up this file here. It should open in a web browser. It's called Radiocarbon Workshop Notebook.nb.html. Hopefully you can see this okay. This just contains some code as to how to run a basic age depth model and how to create a basic special regression model for those data that I was just showing you. It uses a package called Bchron, which I wrote for doing age depth modeling. The first time you run it, you need to install the package Bchron. I won't talk through all of this because I'll be way over my 20 minutes, but I'll just show you some of the highlights of the kind of things you can do. So the first thing that Bchron does is that it calibrates radiocarbon dates. It includes the latest calibration curves, but you can have older calibration curves if you want to, or you can even create your own user-defined calibration curves if you want. If you calibrate, so here I've calibrated a date that I've made up, which I've called it OX123456 for its ID. It's 11,553 years ago with uncertainty 230, but you can play around with these. It produces a highest density region. So remember, it's not a normal distribution. So you can't just have, it's not just got one confidence interval. It will actually break the confidence interval up into segments for where the highest bits of the probability are for that calibrated date. If you give it more dates and you give it depths as well, you can create these basic age depth plots. So for example, here I've just calibrated 2 dates, one of which I've said needed calibration and the other one was just a normal date, so it didn't need calibration. And then I've plotted it and I've given it some axis labels here. And you can see that it's plotted those two dates on there. And that was how I created that plot of the example core, where all of the different dates were shown as you go down the core. It was created using exactly this command, this kind of command here, with slightly different data. Once you've got the hang of calibrating radiocarbon dates, and Bchron can calibrate thousands of radiocarbon dates very, very quickly, you can then run the age depth models. And this is where things get a little bit more slow because the maths gets a lot heavier here. This is the data set. It comes with the Bchron package. You've already seen it in the slides, so this is, you can have another look, a closer look at it in this little workbook. If you want to, you can see the different ages, the HSDs, the calibration curves, etc. And then the way you fit it in Bchron is you call the Bchronology function. So here I'm saying I want to use the test cron data set, which is the thing we were just looking at above. These are the ages, these are the age standard deviations, these are the calibration curves and so on. And down at the bottom, I've got an option for predict positions, which is where I want to be able to predict my my depths, where I want to get predicted ages. And here I've just put a sequence from 0 to 162 centimeters. But when I run this properly, what I'm going to need to do is put in here the depths of my sea level markers, because that's where I want to be able to predict for the different ages. And if I just pop down a bit, so here down here, if you look, now here's my, here I've plotted the output of that chronology, and you can see you've got exactly the plot that we had in the slides as well, with a nice curve and a nice ribbon of uncertainty that goes through all of the dates very, very neatly. Once you've got that kind of thing, we can then combine it with the relative sea level data. And again, the data set comes with Bchron, and you've already seen it. So for each of these depths, 3.5, 4.5, 5.5, 6.5 centimeters, and so on, we've got an estimate of sea level, and we've got an estimate of the uncertainty in the sea level. And now we're going to recreate our chronology, but this time, look, for the predict positions, we're going to use the depths from the sea level data set. So this is going to run our age depth model, but it's going to produce predictions at the depths that we really care about for the to match the sea level markers to the depths. And then there's another function called Bchron RSL, which will fit clever versions of linear regression. So as I said at the start, we need special regression models to take account of both the vertical and the horizontal uncertainty. This function here doesn't fit fancy nonlinear ones. You'll learn about that later. It just fits either linear, quadratic, or cubic regression models. And here I put degree equals 3, which means it's going to fit a cubic regression model whilst taking account of both the RSL uncertainty and also the chronological uncertainty from the chronology we just created up here. And if you do this, it will produce some median, lower, and upper confidence estimates of the sea level for every single depth. So here I've just told it I want It's from 0 to 2000 every 250 years, and it will produce that for me. But I can also do things like plotting the sea level curve. So here again is plotting the output of my cubic regression, taking account of all my uncertainties. My little circles are my data points here, and the line and the dashed line are my uncertainty intervals around it. And this one also does something that's very slightly fancier as well. You can actually change the type to be the rate. So if you wanted to get an estimate of the rate of sea level rise going back in time, you can do that as well. So now we've got the rate in millimeters per year across time, and we've got uncertainties in the rate of sea level rise as well. Again, this is just for a very basic cubic regression, which is not necessarily the best thing for your data. And that plot that I showed you right at the very beginning of my slides is a far fancier version of these kind of models. But really, all it does, just to finish off, how it works is that you take your data, which has depth and ages, and you run it through an age depth model. And then that age depth model allows you to get the ages of every single depth in your core. You take your data set of sea level markers, and now you've got estimates of age for each one of those sea level markers. And you use a special regression model to plot a nice curve through those, which takes account of the uncertainty. Right, that was a very whistle-stop tour of how to create sea level curves and age depth models and where radiocarbon dating fits into all of this. Very happy to chat more with you all about this. Looking forward to the Q&A session, which is coming up soon. And hopefully you enjoyed the talk, and I hope you got something out of it. Thank you very, very much.